Dobrodošli svima. This will be in English because of not only our guests but people online. I hope we are live online and people can see us there. I would like to wish you welcome to this meetup and also welcome to the guys who are here online to our offices. I'm happy to kick off the series of United.Cloud Tech Talks. Basically, it's a series of meetups we'll be holding once each month because we want to really share the knowledge and basically we would mostly like to share the custom knowledge of what our team, something which is unique at least in the region and in our industry. And I'm very happy that we are kicking off with something which is the core or the backbone of any media platform, and this is coding and streaming, and something that United.Cloud is definitely pioneering in the technology in terms of we are doing our own encoding. Most of the other media platforms are basically hiring other vendors, using encoders, configuring them, while we did it on our own. Of course, everything has advantages, but a lot of effort and a lot of gains we also gained there, a lot of knowledge, and we wanted to kind of share that, which not a lot of people know, that we have our own IP there. So, welcome. This is the first meeting of our coding, and we have our guest from abroad, Ozer, one of the authorities on streaming media and media streaming, and somebody who done a lot of comparison articles. But I want to kick off with our senior product manager and the guy who is in charge of our products in encoding, who share also what we're doing and maybe some news what we'll be doing in the future. So, Boban, come.
Hello, everyone. Thank you, Peter, for introduction. I will share the stage with our friend Jenny Ozer and Nemanja Krivokapić, who is also responsible for Headend. I'm Boban Kasalić, product manager for Headend product line here in United.Cloud. So, probably most of you know United.Cloud is a company which develops multi-screen application, which is apparently true. That application we know as a TV 2.0 on the brand name E01. And that application daily uses almost 2 million of devices. That is a huge number. But I won't speak about that because you know that. Probably most of you don't know that we are developing end-to-end streaming solution. And by that, I mean in full backend of that application. And I believe that we are pretty much unique in the region. There are some companies that develop streaming for the distribution, but almost no company that develop its own encoding solution. And our encoding solution lies of 1,000 of servers. That's why we are unique, and that is the topic of today's meetup. I will just briefly go through a couple of slides for you who doesn't know too much about a video, doesn't know too much about encoding itself. Briefly, high level, simplify the things. I used to simplify everything. So, let's talk a little bit why do we need encoding? Why is it so important? Let's see how many data we would need to have if we don't have encoding. You can see that any kind of video we can divide it into frames, and the minimal number of frames per second that human visual system recognizes as a continuous video without interruption is 25. There are some standards with 30, 50, or 60, but let's keep it simple, 25. Each of these frames, we can divide it into smaller pieces, some blocks, and the smallest box is pixel. And number of pixels per each frame depends on resolution of the video. Each of the pixel we can record by the three main colors, red, green, and blue. And you know that in the spectrum, all the colors in the spectrum can be made by those three colors. So what's happening with this analog picture? We digitalize it. If we code each of these colors with 8 bits, and that is one of the standards, it could be also 10. Now there, you see 25 frames multiplying the resolution, and I use the resolution for HD video, and 24 bits per each pixels. That means that we need 1.2 gigabits per second to transfer uncompressed video. There is no telco infrastructure to the end customers that can support such a huge amount of data. And that's why we need encoding. Let's just simplify the things, how usually encoding works. First, the video is divided into the frames divided into the slices, each slice is divided into macro blocks and blocks. Blocks consist of some pixels. Okay. On the level of box, we are doing, let's say, first compression. Sometimes we call it intra-frame compression. How we do this compression? All codecs use some kind of a transformation, and I will very simplify the things, how usually transformation done. You can see this very complicated mathematical formula here, and that is, let's say, discrete cosinus transformation. I will simplify this formula. Down there, you can see what this formula do. This transfer the pixels from the spatial 2D domain into a frequency domain. So here you can see that the values are all around that block. And on the right side, in the frequency domain, you see that all the values are concentrated in the one corner. So there is an idea. Why should we just transfer this part of the spectrum of the frequency domain to the reception side? And on the reception side, we used inverse cosinus transformation. And by keeping just those pixels, we can reproduce almost all picture, depending on the bit rate which we're using on the transfer. Those are the basics for almost every kind of codec. There were some attempts, let's say, with some other transformations, such as wavelet transformation. BBC 15 years ago used wavelet in their codec called Dirac, but without success. All transformation do the same. Do transformation from spatial domain into frequency domain. And then we just keep a couple of those values in the transfer. And this is really intra-frame prediction. Another compression. Another compression which we do is inter-frame compression. Let's explain on this way. If we, for example, if camera in front of me, all things around me are statics. Why do I need to transfer all the pixels if they are not changing? I will just transfer in some frames the pixels over my mouth, okay? And then, by using something that we call motion vector on those blocks which we already made, we can reproduce the picture without a problem. Now you see this scene, and you see this phase here changing. There are all motion vectors on this side. And on the part of the screen where is no motion vector, nothing happens. I don't need any data here in a couple of frames. How we do that? This is group of picture. Let's say in 1 second, we can pick up first frame to be original frame, E frame, or information frame. And after, let's say, 15 or 20, one also original frame. All frames between those two are made with consist just of the motion. There is no static fields, just motion vector, what has really changed. And we have two possible frames. One is prediction and B prediction, depending on from what side do this kind of prediction. And this is also the same for most of the codecs we use today. And by this, and using interframe prediction, we can compress the data more than 100 times, even 200. Let's quickly go what can be the differences and the basic differences between the codecs. There are, let's say, a lot of number of codecs, and when the MPEG came into the industry somewhere in the 90s, MPEG 2 was, let's say, first big boom with the codec. MPEG used the block, which I explained on the first slide, 60 by 16 pixels, and it was static. With H.264, that was the next generation of codec, it introduced a variable block size that can go from 4 by 4 pixels to 16 by 16. Okay? And you can see how this picture is analyzed with H.264. Introducing an HAVC keeps the variable blocks, but introduce even higher block that can be 64 by 64. So what that means? That means the H.265 or HAVC can be more efficient if the picture in some area is static or have no too much details. So you can see the difference. There is no 64 by 64, and on the right side there are some. The efficiency stays on the matter of block, because on this block we can do those kind of transformation and lowering the data very effectively. And let's see the differences between HAVC and E01. There are a lot of others, but I really want to simplify the things, because those things are the biggest let's say, impact on the codecs. On the left side, you can see, yes, 64 by 64. E01 introduced even higher block, which can be 128 by 128. That means that E01 can be even more efficient than HAVC, depending on the quality of the picture, depending on the resolution of the picture. If the resolution is higher, it is more efficient for UHD, for 8K, really. But down there you can see this analysis. For HAVC, there is 33 intra-predicted direction. The way how the algorithm divide those blocks, how do some sampling. And with E01, there are 56, so really more complicated to analyze the picture and needs more CPU. And that is the real game. That is the game with all kinds of codecs, and we in United.Cloud deal with that. How to reach more efficient codec by using existing CPU, because more efficient codecs needs more CPU. And that's all I want to point out. There are a lot of other things that can be mentioned in this analysis, but I will stop here because I believe I need a lot of days for that. So thank you, and John, please. Oh, you have my phone.
Okay, that's distracting. There's like a millisecond difference between when I talk and when I hear it. We'll soldier through. So let me say thank you. This has been a great trip so far, and I've really enjoyed my time. First time in Serbia. It's always, I've worked with the company for a long, long time now, and it's great to meet the people here in person. I've met Boban several times at trade shows in the past. So I'm going to talk a little bit about AV1, which is one of the compression technologies that Boban talked about. And then I'm going to talk about how to produce live streaming. And there's going to be some interplay between AV1 and the live streaming, but it's not totally about AV1. And this part, where is AV1 quality-wise? So, why do we want to introduce a new compression technology? Because it's more efficient, because streaming publishers pay for bandwidth, and the more we can reduce their bandwidth with more efficient codecs, the less they have to pay for their bandwidth. So that's why there's this continual push to introduce new codecs. We're also, 5 years ago, we were working with 1080p video. Now we're working with 4K video. Soon we'll work with 8K video. And we need to compress that down to bandwidths where publishers can affordably send it to their viewers and to where viewers have connections that can play the video. So that's kind of what we're doing. And question, where is AV1 quality-wise? How much do new codecs actually save you? Where are we with AV1 deployment-wise? Is AV1 royalty-free? And then the optimal approach to live transcoding. So most of this is about AV1, and this is primarily about H.264 and HEVC, because I think, as you'll see, most of the live transcoding is happening around those codecs today. So the big answer for AV1 quality-wise is it depends. And we're going to look at 3 recently produced compression technology comparisons. So I've done studies in the past where I compared the quality of the different codecs, and I wanted to look outside and look at some more recent analyses for comparing open source codecs and FFmpeg. So FFmpeg is a developer's tool. It comes with its own compression technologies. Now, the thing to understand about all of these compression technologies, H.264, HEVC, AV1, is that there's not just a single codec. There's a standard, and then any number of technology companies can build their own version of codecs. So there's probably 40 H.264 codecs out there. There's probably 40 HEVC codecs out there. Some are hardware, some are software, some are accessible in FFmpeg, which is a free open source tool. Some are only available for licensing. So the companies who are codec developers, they develop these technologies, they sell them to companies like United.Cloud, like other companies, because they deliver more efficiency than what you get for free in FFmpeg. Now, these are primarily for VOD, video on demand, so what Netflix does, right, or what it does mostly, which is, encode video in the lab that's, it's been filmed, been sent to them in files, and then distributed out on demand. Live is a different animal because you need to distribute your video live. You can't take time to encode it because you've got to deliver it in real time. So the technologies that you use here and here can't be used for live. These are typically called transcoding technologies, and we'll see a few examples. We'll look at FPGAs, which are field programmable gate arrays. That's one hardware technology. And we'll look at ASICs, which is application-specific integrated circuits. That's another. We'll also look at GPUs. So why do we care about AV1 quality? We care about AV1 quality because we don't want to implement a new codec unless it's going to deliver the bandwidth savings I talked about a few minutes ago. So here are the 3 studies that we talked about. Now, X.264 is the technology that everybody's using today. It's been it was developed in 2003. It was the first codec you could use with iPhones and iPod Touches. It was the first codec you could use in smart TVs. It's in a lot of broadcast setups. So probably 95% of the video on the web is in H.264. And then next up is HEVC. HEVC is also called X.265 because there are 2 standards bodies that contributed to the standard. There's the MPEG standard, And then there's the ITU, the International Telecommunications Union. The ITU uses numbers, MPEG uses names, so X.265 is an HEVC codec. H.265 is the standard. So this is X.264, same thing. This is an H.264 codec that's under the H.264 standard, but it's actually the open source X.265 codec that's in FFmpeg. Does that make sense? Everybody nod if it makes sense. Thank you. So this review, and I'll have links to all these reviews in the in a second. This review looked at FFmpeg codecs. This is what you get for free. So they looked at 3 codecs. They looked at X.264, X.265, actually 4 codecs, SVT AV1, and then VVENC, which is VVC. So these are all codecs you can access for free in FFmpeg. And they benchmarked everything around X.265 because that's a codec that a lot of people are using. And basically, you know, if you could deliver X quality at 4 megabits per second with X.265, with X.264, you'd have to boost the data rate by 70% to get the same quality. So that's what these numbers do. It's relative efficiency. So with X.265, if you produce using SVT AV1, you can produce the same quality as X.265 at a 25% bitrate reduction. And then VVC, which is the newest codec available, you can reduce by 53%. So that's what these numbers mean. And so this is study 1, and open source, again, video on demand. Study 2 is from a company called, actually it's not a company, it's Moscow State University. Very famous developer in the video world. They produced a tool that United.Cloud uses called the Video Quality Measurement Tool. It's something I use a lot as well. But they do a lot of extensive codec studies. Now what's important to, the big question on the table now is how efficient is AV1? And the point that I'm making is it depends, because it depends on which codecs the developer looked at, or the analysis looked at, how they configured those codecs during the analysis, what videos they encoded, and how they measured the quality. So these guys made a bunch of configuration decisions, and looking at some of the same codecs, the Moscow State University made different configuration decisions. So they may have used the medium preset with X.264. They used the very fast preset with X.264. Completely different results. And so even though the numbers, they look like they should line up, they really don't. And that's why I keep saying it depends. We don't know where AV1 quality is. Well, so we're seeing X.264, instead of being 170% of X.265, you have to boost the bit rate by 246%. And X.265, again, they benchmarked with this at 100. They found that the most efficient H.265 codec was more efficient than X.265 by about 57%. And looking at AV1, they found SVT AV1 to be pretty similar, no difference here, but they found another AV1 codec that delivered much greater efficiency. So again, what is the state of AV1 efficiency? It really depends on which study you look at, which codec you use, how you test that codec. And then finally, we look at hardware. Now, as I mentioned a few minutes ago, hardware is different because you have to do it live. You don't have the ability to take as much time as you want to encode the file. So the most efficient H.265, so again, the Moscow State University team focused on X.265 at 100%, but they found that the most efficient H.264 implementation was only 20% less efficient. which means that you're only going to save about 20% bandwidth by going from H.264 to HEVC. Why is that? Because it takes longer to get hardware working efficiently than it does software. The hardware that ships today was taped out 4 years ago, because that's how long it takes to develop ASICs, to get ASICs to market, to get them in tools, and to get them working. So, you know, if you came here thinking, gosh, I want to do live AV1 tomorrow, you're going to be disappointed. If you looked at these numbers and said, well, gosh, the most efficient AV1 can deliver something like 63% lower bit rate than HEVC, that's fine in software for VOD if you license the technology from the company who produced it. On the other way, from a hardware perspective, the most efficient AV1 technology is only 10% more efficient than what you get here. And it's actually less efficient than the most efficient HEVC technology. So here, HEVC is much more efficient than AV1 for live transcoding. Here, AV1 is significantly better than or it's 5% better, and here it's 25% more efficient. So if I'm looking at a live application, I'm thinking, you know, I may want to stick with HEVC here for a while because AV1's not going to deliver any benefit, not going to save me any bandwidth, not going to save my customers any bandwidth. Now, that may change with the next release of AV1 encoding hardware, but this is a report that MSU put out within the last 3 or 4 months. It does include the technology that you have in-house, the NetInt product. It does not include a new product from AMD that also does AV1 encoding. So again, big question, first question on the table was, what's the relative efficiency of AV1? It depends. If you use open source technology, it's 25% more efficient than HEVC. If you use licensed available software, again for VOD, it's about 5% more efficient than the best HEVC. If you want to use live technologies, it's about 15% less efficient than HEVC. And I wrote an article about this that you can find on my website here. So the bottom line about quality, and this was kind of the lesson in the article, is that every comparison is implementation specific. You don't want to read an article and says, well, it says here that AV1 is 25% more efficient, let's use it. You have to get the codec in, you have to understand the parameters you use for encoding, and you'll have to compare that to the other codecs you have before you can make that decision. You can't just look at any study and say, well, AV1 is this much more efficient than any other technology. And then the other point is that hardware implementations take longer to perfect. We saw a much more efficient encoding job with AV1 and software than we did in hardware. Why? Because today's cards were taped out in 2021, 3 years ago. Okay, how much codec will how much bandwidth will a new codec save you? That depends, and this is a different question than the codec question. A little bit about bandwidth. Services pay to deliver their video. Amazon, their lowest price for delivery, if you're the biggest user of their CDN services, is around 2 cents per gigabyte. An hour of video encoded with H.264 is about 2 gigabytes of video. So it costs Netflix, or let me not use Netflix because they have their own content delivery network, but if I'm using Amazon to deliver my videos and I'm their largest customer, it costs me about 4 cents to deliver 1 hour of video. Now, if I can get 50% reduction in bandwidth, it should cut my cost from 4 cents to 2 cents. And so this is a different presentation of the data from the first article that we talked about, the one that looked at open source. And basically the presentation of data here says, if I'm using H.264 today, H.265 is going to save me 41%, AV1 is going to save me 43%, and H.266 or VVC is going to save me 66%. Okay, so you're thinking, well, gosh, that's great. Let's just implement these new codecs. And it sounds great, but the savings are only on the top rung of the encoding ladder. So what we have here are two encoding ladders for H.264 and HEVC. And whenever you distribute video, whether it's VOD or live, you typically break it into what's called an encoding ladder. And we've all seen this in YouTube, right? You can click down and pick whether you want the 4K version or the 360p version. And that relates back to how adaptive bitrate technologies work. But this is the encoding ladder you might use for H.264. And if you use HEVC video, you can cut the bitrate. So here at 640 by 360, Apple is saying use 365 kilobits per second. Here with HEVC, it's saying use half that. That's great, half the savings. For 1080p, for 720p, it's 3 megabits per second. Here, it's reduced by about 20%. But the point is, when I connect to a service like YouTube, I might have 5 megabits of bandwidth. So if I get 5 megabits per bandwidth, I'm going to play this file here. The service is going to have to distribute me video at 4,500 kilobits per second. If I connect at 5 megabits here, I'm going to get this file. So the company is sending me the same amount of data. It's just getting a little bit better experience because HEVC is going to be higher quality. The only time you recognize savings is when you're sending the top rung on the encoding ladder. So here, if I was sending it to someone in their home and they had unlimited bandwidth, instead of sending them 7,800, I'm sending them 5,800. I'm going to save the bandwidth. But anywhere underneath the top rung, you don't get savings. You get a better experience. And that's great, right? But the thing is, if you tell your boss, let's implement HEVC or AV1 because we're going to save 40%, but you're distributing to mobile devices in here, you're not going to save any money. Your customers may be happy because the video is going to look better, but they're not, your customers aren't going to, or the streaming services aren't going to be able to reduce their bandwidth. Does that make sense? So you really need to analyze which rung on your encoding ladders you're delivering. So we talked over the last couple of days that, and I don't know how pervasive this is in your service, but we talked about mostly it's the top rung. And if it is the top rung, which it is if you're delivering to the home, then you're going to save the 43% that we looked at a few slides ago. On the other hand, if you're delivering to mobile devices or you're delivering over sketchy connections, then you're not going to get that bandwidth savings. You're just going to deliver better quality video. And QoE is quality of experience. So it's nice improving the quality experience, but again, that won't help you if your boss is expecting a 40% drop in bandwidth costs. And then a couple of other points. You know, the 43% sounds great, but the savings are only for devices that support the new codec. So today, we're going to look at some of these numbers in a second. Only about 8% of mobile phones support AV1 codec. So if you use AV1, you're only getting 8% savings on those devices. Now there's more browser-based viewers that support it, and there's a lot of smart TVs that support it, but if you're primarily distributing to mobile, you're only going to get the benefit for those companies that are delivering to devices that support it. In addition, encoding and storage costs are additive. Everybody's doing H.264. If you decide to implement HEVC or you decide to implement AV1, you've got to encode that, and that's a separate encoding cost. You've got to store that. That's a separate storage cost as well. So it's not like you're saving any money on the encoding and storage by using a higher efficient codec, because you're going to have to support both codecs in the short and long term. The encoding costs are going to be higher. Boban talked about the fact that newer codecs are more complex. That means it takes longer. It means it costs more to encode them. And then again, you still have to encode and store your older codecs to support the legacy devices. In addition, you know, when I started looking at streaming video, the cost per gigabyte that I just said was 2 seconds for AWS was around 50 cents per gigabyte. So the costs have dropped by a factor of 25 to 1, and that makes the savings much harder to harvest, right? You used to save, you know, 25 cents per gigabyte. if you cut bandwidth costs by 50%. Now you're saving 2 cents per gigabyte. So the costs that you get back aren't going to be as significant as they used to be. And then none of this is easy because your player doesn't natively support AV1. If you've been playing H.264, you've got to make sure that your player supports AV1. Your entire infrastructure supports AV1. You've got to add AV1 encoding to your encoding stack. You've got to add it to your player stack. So there's a lot of expensive development that goes into supporting a new compression technology. So the bottom line for me, and we'll cover this a little bit more in a second, is that you see fast codec adoption when it gets developers into new markets. When H.264 came out in 2003, it was instantly deployed in TV sets. And then in 2007, 2008, it was deployed in Flash, and then it was deployed in all Apple devices. And soon everybody dropped every other codec, and they started supporting H.264. It was a universal codec. When HEVC came out in 2013, that's when we started to see 4K TVs. 2 years later, HDR came out, high dynamic range, and all of a sudden you had to have H.264. It was very quickly adopted because it got you into new markets. If you're Netflix and people are buying 4K TV sets with HDR, you need to supply 4K video with HDR, and the only way to do that was HEVC. And then if you're a Netflix competitor, you had to do the same. If you're Prime, if you're Hulu, and if you're, if Sony comes out with the 4K HDR TV and you're Philips, you've got to come out with one. So these technologies really benefited from opening up new markets that weren't previously accessible. And with AV1 and VVC, all they offer is bandwidth savings. There's no new market to get into. They may play on 4K TVs, but you can already play on 4K TVs with HEVC. So, HEVC came out in 2013, and it was widely adopted by 2015 or so. AV1 came out in 2018. It's 2024, and you'll see in a few slides that it's very slowly adopted by any company that's not in the Alliance for Open Media, which is the group that sponsored it. So, I've been looking at this for a long time, and companies tend not to support new codecs strictly for the bandwidth savings. You've got to be very big to do that, and you'll see an example of that in a second. So the realities of AV1 adoption. We'll look at the AO Media Promise. They talked about a 2-year development cycle. We'll look at the optimal reality, which is 5 to 6 years best case, and then we'll look at where we are today. So this is what AO Media promised us. The standard was, the group was launched in 2015. This was when the codec was launched, and they said it would take us 1 year to get to integrated circuits hardware, so you get a chip, and then 2 years to get to full support here. So they had, the TVs, they had mobile devices, they had other devices that could play AV1 video. So basically 2 years, and I'm sorry, this is 1 year to software, this should be 2 years to hardware. Now let's look at the realistic case for hardware adoption. So spec is finalized, and this is the starting gate. This is year 0. Now chip vendors have to start development. When I say chip vendors, I mean Intel, NVIDIA, the companies who make the chips that go on our mobile phones, Broadcom's, a lot of others. So they start developing, and their chip launches in 1 year. So 1 year after that, we start to see consumer products come out. We start to see the televisions, we start to see the mobile devices, because they can't start development until this chip is done. Then what happens? You need a critical mass of products out there before you want to support a new codec. And that can take anywhere from year 2 to year 6 until you have enough devices out there to even want to support. So it's a 4 to 6 year cycle, best case. Now let's look at and see what happened with AV1. AV1 came out in April 2018, right around NAB. Chip vendors started, chips were available, and everything got delayed in here because we had the pandemic, we had supply chain issues, and we had Apple sitting on the fence and not supporting AV1 in their mobile hardware until last year. So where are we today? What number do we care about? This is a report from, you can see the URL here, where they basically say that before a company should consider a new codec, it should be supported by 30% of the target market. That means 30% of browsers, 30% of mobile devices, and 30% of smart devices in the home. So this is from the same report, and this is a report from Interdigital, and you saw the URL. Interdigital is a company that's got a lot of HEVC patents. It's fair to say they're not friendly to AV1, but they're a public company, and you have to trust what they say. And what they're showing here is they're showing the codec adoption by most of the significant over-the-top content distributors of premium content and some UGC down here. And what we see, as I said, everybody does H.264. Why? I mean, that's table stakes. You got to play on the old iPad that your mother-in-law may have. You have to play on the first smart TV that anybody ever owned. And then most companies support H.265 and HEVC. Why? 4K HDR. Now we go to VP9, which is an intermediate codec. I'm not going to spend any time on. And then we go to AV1 here. And we see that the only companies that support AV1 are Netflix and YouTube. Now, what do Netflix and YouTube have in common? They're both members of the Alliance for Open Media. So they're founding members of the group who founded this new technologies. Of course, they're going to support it. Meta is another AO member, another AO Media member, and they support it pretty heavily in their Reels feature. But there's no independent company who's not a member of AO Media that supports AV1. And this is June 2023, so this is a bit over a year ago. And you've got Apple TV, you've got Amazon Prime. Amazon is a member of AO Media. Apple's a member of AO Media. You've got Disney, HBO Max, Hulu, and Paramount. So there's not a big rush to support AV1, and we'll see why in a second. But it is known that Hulu and Amazon are considering AV1 at this point. But again, we're 6 years after the standard was launched. AO Media promised us a 2-year adoption cycle. So where are we? We see in the browser that compatibility, and this is from a website called Can I Use, is at around 90.69%. So it's well over the 30%. The problem is premium content distributors don't care about the browser. Much of the video that their customers watch are either on mobile devices or on smart TVs in the home. So they don't even care about the fact that their video is going to play on those devices. On mobile, as I mentioned a few minutes ago, AV1 penetration is only 9.76% with hardware playback on mobile. So if you're considering AV1 and you're targeting mobile devices, then you're thinking, well, goodness, we're nowhere near the 30% that's relevant for me wanting to start supporting it. And then if you look at the home, the numbers aren't as clear. There's a lot of data out there that says we're close to the 30%. And as I said, Hulu and Prime are starting to consider AV1. But I think in this particular case, United.Cloud is pretty solid because you guys have your own decoder, and you know that most of the decoders that you have out there support AV1. So I think if you're going to support AV1 for your own client base, or for people who are using your decoders, then I think you're well past the point where it starts to make sense to do that. If you're general purpose distributor, then it's probably again that you really care about this. These numbers should be above 30% at this point. But if you're looking primarily at mobile, then AV1 doesn't make sense even today. Then the next point I wanted to talk about is AV1 royalty-free. When the Alliance for Open Media launched AV1 back in 2018, they were very proud of the fact that it was royalty-free. You didn't have to pay anybody any royalties for for using the codec. And that's very different because we talked about the two standards bodies. We talked about the ITU and the MPEG. If you want to use H.264, HEVC, VVC, you pay a royalty. And we'll see who those royalties or what they're charged for in a moment. But one of the reasons that the Alliance for Open Media wanted to create AV1 was because they didn't want to pay royalties. So when they came out, this is what they said: the open and royalty-free format for the next generation ultra-high definition video. Royalty-free, that was their promise. So the reality is there are two patent pools claiming royalties on AV1. Sysvel, which is in Barcelona now, came out in 2019 with a patent pool, and they started charging royalties on AV1 compatible hardware. And then Avanci is another patent pool owner, came out in 2023, and they started charging royalties on AV1 encoded video for content. Now, AO Media doesn't charge a royalty for AV1 usage. You can license it from AV1 royalty. You can license it from AO Media royalty free. But if you do that and you have any AV1 intellectual property, you have any patents that relate to AV1, you have to contribute them to the pool for free. And AO Media won't indemnify you if you use AV1 and then you get sued. Okay? So if Sysvel sues a company for using AV1, they can't go back to AO Media and said, hey, it's royalty free. They basically just have to pay the royalty, and they don't have any right to get anything paid for via AO Media. So this is patent pool. This is groups of patent owners who get together to start asking for royalties on the technologies they've developed. Companies don't have to join a patent pool. They can go out directly to large customers and try and license them directly. So what happened here is that Broadcom sued Netflix in Germany for using HEVC video. Now, this license here is mostly for hardware. It's for hardware encoders, hardware decoders, and that's what royalties have typically been on. This was the first case I'm aware of where Broadcom sued and said, we're not suing you for buying encoders or buying decoders, we're suing you for encoding an HEVC and distributing that format. That's violating our royalties. And the German courts agreed. What that means is that if you're a content publisher at this point, you can be sued by any owner of any compression technology IP based upon the same theory. And we're going to look at some, some examples of that, including the fact that Nokia sued Amazon and HP for HEVC content. And again, if they win, it's likely that all content encoded with any codec could be subject to a royalty. And then if you look at the AO Media site, they no longer say it's royalty free. They said there's no royalty on the license that we give you, but they don't claim that AV1 is a royalty free codec. So what's this mean? Pre-2023, the only companies paying a license for any codecs were encoding vendors, and they were paying for hardware encoders that they manufactured or software encoders, and player vendors, whether it was browser, mobile, OTT, or smart TVs. So Apple is paying a royalty for HEVC in all the smartphones that it produces with HEVC playback. And that's the typical target for patent pools. In 2023 and beyond, again, the encoding and player vendors, these guys are going to end up paying royalties. But all companies streaming encoded videos may also owe a royalty, some via the Avanci patent pool and some via other pools in private litigation. So the landscape has changed, and it's not just for AV1. I'm not singling out AV1, it's for any codec at this point. So the patent owners are really going after streaming companies. Now, what does this mean? I think very little in the short term. We're going to see companies going after the big companies before they go after the smaller companies. But as a practical matter, before you adopt a new codec, if you're a publisher, I think you really need to talk to your legal people and say, what are the implications for us financially? And this is the first lawsuit we talked about. This is 2023, so it's a relatively new phenomenon. This is November 2023. This is Nokia sues Amazon. This is the licensing official from Nokia, and this is 3 months ago. So this is July 2024 saying, hey, we licensed our compression technology to a major streaming service. And then a week ago, he said, we've got another major streaming service. So I think content royalties are coming to the codec world. And that's just, it's just kind of an unfortunate fact of life. Okay, so let's change gears, moving away from AV1, and let's start to look at the economics of large-scale transcodings. And here we're going to look at two articles that I've written in the past. One relates to a live interactive application, a company called Mayflower, and then we're going to look at real quickly at a review that I contributed to in streaming media. And the big question is, how much does hardware transcoding save you when it comes to large-scale interactive or even broadcast applications? So this is a company called Mayflower, and they do interactive video, gambling, gaming, that type of video. And so this is what I call many to few. So they have a lot of people coming in, sending video streams in, and they go out to relatively few, maybe 10 or 20 people each, as opposed to the typical broadcast schema where you have one stream that might go to thousands of viewers. So it's a little bit different than the traditional broadcast scenario. But they are using, they got WebRTC going in, they are using FFmpeg as their encoding stack, and then they're building an encoding ladder that looks like this, and they're streaming it out. The requirements are pretty significant. They've got 10,000 incoming streams, 1 million outgoing streams, latency has to be under 2 seconds, and as I said, they're using FFmpeg. So they said, okay, what's the most efficient way to do this? They started, like everybody, using CPU only. So they used FFmpeg, they used FFmpeg-based open source codecs, and they spent $20,000 per CPU, per server, and in order to do the 10,000 incoming streams to the 1 million viewers that they were reaching, they had to buy 500 servers to produce those ladders. Then they went to GPUs. This is the NVIDIA T4 GPU, and that reduced the required servers to 105. And I'm kind of skipping through this. We've got a nice summary slide that does a good job with that. They looked at, and this was when I worked at NetInt, they did our first generation ASIC-based transcoder. That cut the number of required servers from 500 to 67. And then the second generation, the Quadra, which is the unit that you all have, they only required 38 servers to do the same number of streams as they did with the CPU. So if you look at the overall cost structure, the server cost, including the cards, this is what you see here. The cost per stream went from $1,000 per stream to $141. The CapEx, how much capital they had to spend to equip their servers to do this, went from 10 million to 1.44. The co-location cost to house the servers went from 750 to 57, and the total power that they spent went from 325 to 33. Long story short, if you're doing a lot of live type broadcast applications or even interactive applications, you can't use software. You really have to consider hardware type transcoding. And what about quality? I think it's important to understand what the quality level is for software as opposed to hardware. Software is for VOD, video on demand, and low volume transcoding in most instances. Hardware is for high volume transcoding, but probably not the World Cup. If you're encoding a very large scale event that's going to be viewed by millions of viewers, you probably want to figure out a better way to encode it from a quality perspective than using hardware. And let me explain what I mean. And this is looking at H.264 and HEVC. So anybody who's used X.264 knows that you get to choose different presets. This is the ultra-fast preset. The yellow indicator is the time. The top line indicator is overall quality. The red indicator is low frame quality, which is a measure of transient quality problems. So we see that with the ultra-fast preset, it encodes in 5% of the time as placebo, but it only delivers 94.7% of the quality. And this is low resource, lower quality. This is balanced resource, balanced quality. And this is resource intensive, diminishing returns. And if you look at where VOD is, video on demand is primarily in here. You want to spend more time encoding your video to get better quality. Live productions, if they're using software-based transcoders like X.264, typically use a preset in the ultra-fast to medium range because they need to get good throughput in their machines. They can't use the higher quality presets because they won't get any throughput. They're going to end up spending a lot more on hardware than they would if they use the lower quality preset. So ASICs target quality in this range. It's not the best quality. It's not good enough for the World Cup or the Super Bowl, but it should be better than the quality that you get if you use these presets that you would normally if you're encoding in software. And this again is from an article that was written by Derek Freeman. I worked with him to make sure he was able to use the product appropriately. And what he found, these are 3 different metrics. This is H.264 video, PSNR, SSIM, VMAF. Green is better, pink is worse. And here, the Quadra, which is the hardware card, was able to deliver better quality than X.264 using the very fast preset. Now, if we used the medium preset or the slow preset, X.264 would have produced better quality, but it would have had no throughput. And that's kind of the point. And then so this is football, this is Meridian, this is a different test clip, more movie-like, and we see the Quadra won in all 3 metrics. So, and then if we look at HEVC, we see kind of the same dynamic. We use the ultra-fast preset because that's what you need to do for HEVC encoded content. HEVC is a more complex encoder. To get good throughput, you've got to use a lower quality preset. And we saw that the Quadra outperformed X.265 significantly in the VMAF score in the football video and in all 3 metrics with the Meridian video. So when people think about hardware transcoding, they automatically think that there might be lower quality that you have to accept. And that's really not the case because in most instances, if you're using software, you're going to have to use a low quality preset anyway. I think that's... So high volume live transcoding needs ASIC-based transcoding, and that's the unit you guys have in the net in Quadra. From a CapEx, OpEx, and environmental perspective, you can save a lot of trees if you use ASIC-based transcoding, particularly for 24/7 programming, interactive type applications. On the other hand, if you were broadcasting a very quality-centric event, you can send a lot of machines at a particular stream, get a higher quality video using software, but it's too expensive to use for these type of applications. So hardware really excels. These type applications, software is good where it's one-to-many, a very high, highly viewed event. That's it.
Okay, let's check if the audio is working. It is. John, thank you very much for this presentation, and I believe that there was a lot of useful resources and information that you just showed. So, hello everyone. My name is Nemanja Krivokapić. I'm a system architect of the Hidden department here at United.Cloud, and I wanted to use this opportunity to present to you what we are doing here in our R&D center. And how we basically solve the issues that both John and Boban was speaking about. So our idea, we exist for the past 8 years as a software development center. And one of the things we learned very quickly is that in the field of video compression and the video encoding and video processing, just having the software engineering knowledge is not enough. This area of expertise is actually a multidisciplinary problem, and we need to have the most multidisciplinary approach. So aside from having good software engineering base, we also need to understand the domain. And this tech talk and others that will follow, one of the goals is to basically get to know each other and get to know the people who are also into this domain, aside from communicating to the community that, hey, there is a company in Serbia who is doing something that the big guys are doing, and we are doing it locally with the local people. So I just wanted to share that. And the idea of this presentation is to show you what we are doing and how we are basically doing it, and what are the challenges that we encounter in our daily work. So I want to start with the clear message that most of the work we are doing here in the United.Cloud is the in-house development of the software components. Basically, we are developing the entire solution used by all of the telco operators inside the United Group. And with that in mind, Boban already mentioned, I just wanted to clarify it, is that in the head-end department, we are basically developing the OTT platform. Now, what is the OTT platform, or at least what are the building blocks and the pillars of this platform? So we have basically 3 products, or at least 3 main products, and that is the encoder, the origin, and the CDN. Up until this point, we spoke only about video compression. I wanted here to point out that video compression by itself and solving that problem is just a piece in a puzzle when you want to bring the business value to the customer, in this case telco operators. You need to gather all the sources, you need to do the processing in a specific way, then you need to pre-record all of that content, and you also need to provide a live streaming experience to your customers. So these 3 pillars are basically the backbone of the entire OTT platform that we develop here. Just to get you to know better our products, so our encoder is a fully software-based encoder that currently support H.264 and H.265 in both MPEG-2 transport stream and the CMAF compliant encapsulation, and also provides the ISO-defined DRM encryption scheme. When we are talking about our origin, on the next slide you'll have a chance to see the scale of the operation. This origin component is basically in charge of keeping all the catch-up recordings of all the channels that we publish to our customers, so that they can watch that TV show or a series when they get back from work, or they decide to chill out for an hour or 2. And the third component is a CDN, which is a fully custom developed here, so we are not using the CDN providers. We have our own CDN, which is developed here in the United.Cloud, that is basically used to deliver all that content to our customers. Okay, just to give you the idea of the scale of operations that we cover with our software products, we have 5 production deployments. One is a worldwide deployment, so we have a worldwide telco operation, or at least one worldwide OTT operation. And we also have 6 telco deployments in the countries mentioned below. When we are talking about the encoding scale, we have over 2,000 channels, most of which are the HD channels. We also do streaming of the UHD channels and SD channels. And in terms of the peak traffic, so for example, when there is the World Cup, Football Cup finale, the peak traffic that we need to sustain during those moments is almost over 4 terabits per second. This is achieved from 62 locations using 422 live streamers and around 432 catch-up streamers. So now you have the idea of the scale of operation our software needs to support. And basically that entire solution is based on these technologies. We are using C++ for our encoding processes. We are using Java wherever we can for the streaming processes and also part of the packaging. Our software encoder is of course FFmpeg based, and underneath it uses H.264 and X.265 libraries, which we customize here why we'll see the challenges later on. Java-based packager to support both CMAF and MPEG-2 transport stream packaging. Okay. When we are talking about video compression, most of the people focus on the encoder itself and the FFmpeg. But to bring that technology into life and into a real-world production systems, this is an example of a system that you need to develop for our customers to be able to use that encoder in an optimum way. So basically, when we say encoder, it's not just about the transcoder itself. We need to provide first the video processing pipeline, which consists of the ingester, transcoder, packager, and the publisher. But also we need to provide the management layer inside the encoder itself. So all of these services are running in each and every encoder we have. And as you can see, it's a mix of Java and C++ technologies. And they also integrate with a lot of services that are not part of the encoder, but they are part of the platform. In the end, what we have achieved up until this point is that we have the ingest support for MPEG-2 transport stream over HTTP. We have MPEG-2 transport stream over IGMP-v3. We also support uncompressed signal over SDI. We support multiple packaging formats for VOD. And of course, we do support silence generator, which will be important in the later stage. Okay, in terms of the processing, one of the things we did early on, and it is related to the topic of latency and performance intensity, is the single-in multi-out approach. Basically, we are trying to optimize our processing workflow to use as little resources as possible and to remove any duplication of work where possible. Our processing also support AVC and HAVC compressions. We do support graphic overlay, watermark support, SCSI-35, and dynamic GOP. In terms of packaging, we support both MPEG-2 transport stream transmuxing and CMAF live transmuxing. For CMAF transmuxer, we also provide DRM encryption, which is CPX compliant. And in the output, we do provide progressive MPEG-2 transport stream, HLS output, and also IGMP-v3 with lost packet recovery mechanism. Up until this point, SRT, which is basically the industry standard for the output of the encoder in contribution, is possible only in unicast network environments, so point-to-point. There are some announcements that SRT will support multicast, but up to this point, that's not the case. So one of the things that we developed here in United.Cloud is also a proprietary protocol for the distribution over multicast using MPEG-2 transport stream packages. So as you can see, as we go down from the requirements, there are more and more components and more things that we need to work on our own and to develop them in-house. I just wanted to point out all of the things that at this moment we are providing to all of our customers. Another important thing that I notice when visiting conferences is that the major focus is usually on VOD content. Here we are primarily focused on the live. And the reason for that is, of course, because most of the content we do provide is consumed as a live content. There are some constraints and limitations that we need to be aware and that needs to be addressed that are usually not directly available when you are using the, for example, open source solutions, or they are not performant enough for the large scale operation at hand. So what are the challenges of the live transcoding and live streaming in particular? Well, the first one is the latency. So for those of you who are familiar with the industry, you'll remember that OTT as a technology for streaming live channels is present in the recent 7 to 10 years. Prior to that, the big players were, of course, the broadcast technologies, DVB-C, DVB-2, T2, DVB-S, so satellite, cable, or terrestrial signal. And one of the things they do great is that they have a very low latency glass-to-glass latency for the consumers. OTT was introduced and got its popularity with the OTT services like YouTube and Netflix, which are doing VOD, and the technology itself was more leaning towards the VOD content, not having any latency issues in mind. Another thing is that we need to be aware of the resilience. So if anything that can go wrong will go wrong. Basically, what this means, in lab conditions, we have a very clear, stable input signals receiving. In production environment, it is totally possible that you have the lost packages, that you get corrupted packages, that you get portion of scrambled packages in an unscrambled signal, things like that. And these are the challenges that we need to address. And of course, in the end, as every business, resources are not indefinite, and somebody pays for that resources. So network is a big constraint because all of the telco operations, they have their own networks which are predefined. They have limited capacity, and any extension of the capacity or requesting higher bit rates has a $sign in front that you need to communicate up front. So basically, when providing live streaming and live transcoding solution for our customers, these are the three main challenges that we need to have in mind. Now, of course, you'll ask maybe why quality or the video quality is not one of these three. Well, if you have a high quality video that has latency of 2 minutes, nobody's going to watch it. If you have a high quality video that breaks down every 5 minutes because you have some corrupted packages on the input, nobody's going to pay for that. And also, if you have very high quality video, but your network provider cannot support it at that moment, you're not going to be able to watch it. So these are the preconditions that need to be met before we can deliver the high quality video to our customer, which is, of course, our goal. So how do we address them? Well, in terms of latency, we keep our encoder latency in single-digit numbers. For AVC, it's around 3 seconds. For HAVC, it's around 5 seconds. And this is our main goal. We'll talk more about the quality control later on, but this is our main goal. Because of this, we use only single-pass encoding. We are using constant bitrate encoding mode and not the constant quality factor or constant rate factor, depending which encoder you look into. But basically, we are not using variable bitrate encoder mode. And also, we are trying to use SDI whenever possible before we use the IP as a source. Why? Because if you are using the IP source, then that source is already once encoded, most probably, and you have the additional latency introduced. Whenever possible, if you can use the uncompressed video directly from the studio, you get free savings on the latency. In terms of resilience, we are developing and using existing filters that already exist, and also we have some custom filters implemented by our development team that is basically constantly monitoring and filtering the ingress packets that are coming into the encoder, looking for those corrupted, scrambled packages that we can then basically discard. If possible, without, maybe cause a couple of macro blocks or something, but not disrupting the signal itself. Artificial silence is one of the examples where we, for example, have signals that for any reason suddenly remove or lose their audio component. So in these cases, we needed to introduce the artificial silence generator, which basically generates the silence just so that we can keep the show going. And of course, in the end, if everything else fails, you need to fail fast and cheap. What does this mean? It means that sometimes it's better and cheaper to fail fast, stop the encoding, restart the process, and maybe lose a few seconds of the video, than affect the 2 minutes of video with macro blocks and artifacts that you cannot fix just because the information on the input is not there. And if there is no information on the input, you cannot, rarely you can, but in general, you cannot make it up, so it's lost. When it comes to network, we need to be mindful of the bitrate and keep the balance between the bitrate and the video quality, because the bitrate is constrained due to the network limitations that we have. CBR is an absolute must. You need to be able to predict the bitrate of your content at any given time. How we achieve basically those trade-offs when using CBR with a constrained network? Well, we play with the codec parameters, do a lot of fine-tuning, work with guys like Jan to find the best possible combination to bring the quality to the maximum possible level. And during our learning about encoding, we definitely went for VMAF as a gatekeeper. So we needed to have a single metric that will make sure that all the things we are doing are referenced and compared between each other in a uniform way. Okay, so now that you know the challenges, I just wanted, and John also spoke about different ladders, Apple recommendations and things like that. In our production, after all the testing we've done, these are the ladders that basically we provide to our customers. So we have AVC SD channels, we have AVC and HAVC HD channels, and we have the UHD HAVC channels. Now, when we are streaming UHD channels, what we also do is usually complement it with HAVC HD channel, just to make sure that if there are any degradation in network performance for our users, they can fall back to the lower resolutions and the lower quality streaming, but still get the stream. In terms of the codec libraries, as you can see here for the AVC, of course, it's X264, basically a standard, so a software decoder. For the HAVC, we opted for the SVT HAVC rather than X265. Basically, what we discovered is that SVT HAVC produces much better quality and produces much better quality when it's allowed to spread. And in terms of quality, it produces it with a lesser power and also lesser latency when allowed to scale horizontally on multiple threads. X265 definitely provides better video quality, but in terms of density and because of the algorithms it uses, it cannot scale horizontally and utilize the multi-threaded and multi-CPU applications. So this is what we came with. When we started working on the encoder itself, we relied heavily on manual testing. So basically, we would all gather around in one room in front of the TV, and if we had a new release of the encoder, it would, and I'm totally serious, it would look like we are sitting there watching tennis, Djokovic, and discussing if the image is better or not. And then we would watch another content and another content. Then we figured out, okay, maybe it's not required for all of us to sit and watch that. Maybe we should have the QA who is going to sit down and watch. After 2 or 3 years, we definitely discovered that what happened is that 1 week with one release, we were like, okay, the image is better. Then next week, somebody would come from a side and say, no, this is much worse than the previous one. So there was no reference value that could be repeated every week for every release. So we then agreed that manual testing is not the way to go, and we moved on to automated testing of every release of our encoder. And when you're doing with a VOD, one of the requirements for a test is that it can be repeated, and that when repeated, it will produce the same result. So with VOD, it's much easier because you have a pre-recording that you can put every time through the processing pipeline, measure the PSNR or the VMAF, and then just compare the values. With live, you can do that. Not only that, but also with live, there are different signal providers that we use, all with some specific issues in the signals that we need to handle. And because you saw the number of channels we have in operation, it's not possible to test every release on every single channel. And then even if that would be possible, the question would be for how long? Is it 5 minutes enough? Or do we need to run it for 1 hour? Or do we need to run it for 8 hours or 24 hours or 7 days? And then the question goes on and goes. So we sit down with the development team and basically developed a testing strategy for our encoder. And I want to talk about that now. So we said, okay, what are the three key components that we need to monitor? One is the video quality. Now, in terms of video quality, things are pretty clear. You basically have two ways to go. You have objective metrics and the subjective metrics. You can go with the PSNR or you can go with the VMAF. So we decided to use both, just to give a little bit more priority to the VMAF instead of the PSNR. Why? I'll talk in a slide or two. The second important thing is performance. So basically how encoding works. We say, okay, this encoder can produce that amount of outputs, and we give that sizing to our customers. We need to pay close attention that with new release, we do not change the density requirements, because as every big corporation with that number of channels, if you switch from 5 channels on a single encoder node down to 3, that means you need to increase the number of encoders, which is not something you can do instantly. So second important thing is the performance, and basically we said, okay, we are going to monitor latency, bitrate, and density. So each new release on a set of predefined test vectors will basically look for a baseline in latency, in bitrate, and density, and confirm that we do not have any regressions in those metrics. Third, also important thing is the resilience. And this is something that we are probably having the biggest issues with, because we cannot predict all the variations that can happen in real world when ingressing the signal. So what we are doing constantly is building up our own database of real world samples, usually samples that we had issued before, and building up the database of validation test vectors with the new samples. Okay. So objective or subjective metrics is a discussion that everybody is taking these days, and it depends at what do you look at. So if you're looking from a research standpoint, you will most probably give the objective metrics a bigger go. But if you are looking from a customer standpoint, then for us the imperative is the subjective metrics basically, and following the VMAF and making sure that our pipeline guarantees that VMAF does not go below a certain point that we define, which in industry there is some convention that basically anything between 90, 91, and 95 VMAF score for the top rank profile is considered great quality. Okay, so as I mentioned, we decided that VMAF is basically a metric of satisfaction. It was developed by Netflix. Why is it so good? It's so good because it is doing the full reference. It is a full reference metrics. What does it mean? It means that it looks at the frames as a whole. It means that also it does not execute calculations or per frame independently, but it takes into the consideration also the motion vectors that Boban talked about, and basically gives you the prediction of subjective quality, because when they developed the VMAF, they basically done training on a large set of numbers that they actually hired people to give their feedback about the video quality, and then use that data to train the VMAF model. The issue with VMAF is that it requires frame perfect alignment of input and output. So basically, how does the VMAF work? It takes a frame of a source and a frame of your produced output, and basically compares those two frames. Now, if you lose synchronization between the frames and it starts comparing 2 frames in advance, and you lose that alignment, then your VMAF score doesn't mean anything, because it's not comparing the source frame with the destination frame. Now for VOD, because you have a limited set of frames, you can number them from 0 to whatever the number of frames you have, and then basically you can repeat the test and expect to see the results that you can compare. Now in terms of live, if you would just run a test pipeline or a test or a VMAF tool, you have 2 problems. First, you have a delay between the input and the output. Second, you have no correlation between the frames. And third, every time you start the VMAF tool, another sequence of frames is going on. So the VMAF score you measure now and the VMAF score you measure in 2 hours may not be relevant to each other. They are both relevant metrics, but they are not relevant to each other because the nature of the content can change. Now it can be a TV show, 2 hours after this it can be a game match. This is something that we encountered during HAVC development, and what we did basically, and this is something I'm really proud of the team that worked on this, is that we developed the VMAF aligner solution that with our test vectors can basically do the alignment of the frames, making sure that when we run the VMAF over and over again, the frames that it compares are aligned perfectly, so that we can basically track that VMAF score because we guarantee the sequence of the frame, and we can track that VMAF, and by that we can have a gate that says okay or not okay for the production release. Now, the important thing is, okay, we want to measure all of this, but we also want to be fast from a software development perspective. If we are doing these tests manually, it takes away time for people in the development team to work on a development. So there are some things that we learned as we went through this process. First thing and the most important thing is start small. So basically, if you are making a software, or if you are making an encoder, make sure first it does the compression at all. So don't look at the metrics, the latency, no. You just run the process and see if it produces the output, basically the output that makes sense. In our use case, we basically look at the length. So, okay, if I gave you 5 minutes of video, I want 5 minutes of video on the output. You'll be surprised how often these tests can fail. And to execute them, they are very fast. So basically, you get the feedback very quickly. Also, make sure that the selection of test vectors that you put into these tests represents different use cases from your production. The easiest thing, and that's okay when you start, is to go online and just type test vectors for video encoders, and you'll find a lot of sources that you can use for testing. And some of them are very corrupted streams intentionally made to stress test the encoder and see how your encoder behaves in some extreme situations. But then again, what is the probability that you will encounter that kind of corruption in the streams you are working with? So just make sure you get a good selection of the fewest possible test vectors or pre-recordings from a production that represents different qualities. Don't go only about sport if you also have movie channel and a TV show channel. So just make sure to make a good distribution. Another thing is automate everything. So basically provide your developers or build together with your developers a system where they can focus on software development, and basically whenever they push something to be merged, everything is automated and done while they are doing something else, just providing them with the constant feedback if everything is okay. Another important thing is to always keep the engineers working on the encoder, in the loop, when designing test strategy that you are going to apply. Why? Those are the people who during their development encountered many different situations. They can help you make scalable, fast test strategy that will guarantee you the best possible output quality. Third thing is define metric gateways for each step. So if you say, let's say the classic software development cycle goes like, you have a pre-merge, post-merge, and then release to production. Okay, you'll start with small, so you start with the smoke tests. Define metric gateways. Don't just run the test. I actually saw those situations, not here, but I know that those happens is that there is no error, meaning that everything is okay. It's not the same thing. There can be no error if you have no metric gateway. Your VMAF can go from 95 to 65. I mean, it's still, there's no processing error that will stop the transcoding, but that's not something you want to release to production. So define exact KPIs for each step of the process. Third thing, make your own tools. There was a big discussion among us. Okay, there are tools that we can buy, but what usually happens is that those who are building tools, they are trying to be generic. They are trying to build a tool that can cover wide market and wide number of use cases. Sometimes, for example, with the VMF frame alignment tool, you need to build something by yourself. We are engineers, we can build our own tools. So this is also something that's important. We develop VMF frame alignment tool, we develop mock test vector streaming server with our predefined collection, and we also use tools that exist, but we customize them or wrap them in our own wrappers and then use them inside our pipelines. Anything to avoid human error and manual testing. What we have in the end, so basically, at this point, we do have our build process fully automated. We have metric-driven validation, so nobody is actually sitting down and watching TV and discussing if this video or this version is better than the previous version. And we have shifted our attention together with Boban in terms of quality and reliability. So now that we have the process, we have the metrics defined, we can actually focus on the results of those tests when making some decisions for the future. So that's something I wanted to share with you. Thanks. Since I believe there's no speaker after me, I just want to invite everybody who are present here. I just wanted to mention food, I believe. But of course, if anybody has any questions, I'm here. Especially for the people online. I mean, for the people here, I think it will be easier with food and beer rather than me sitting below these lights. Okay. Thanks, everyone, and let's go for the food and beer.